Hello, my good students. This video is for those that missed the class or want to review, but today we're talking about the introduction to mathematics and number. And so let me share the screen with you. Get pencil and paper ready or your note guide ready. We're going to go fast. If at any time that you need to stop the video, you're free to do that and catch up if you must. But anyway, here we go. You should be able to see my screen now. So what is mathematics? There's lots of different definitions for that, but the one that we're going to use for class is this one. It's the art and the science of number. Now, when I say art, I mean something a bit different than the common usage of the term art. Most of the time people mean art like painting or ballet or something like that. And when they say science, they mean something maybe like chemistry. And I don't mean art and science in terms of subject matter, like what you would study in school or something like that. I mean how or why you're doing the thing. So this goes back kind of to the Renaissance idea of art and science. And art is something that you do to explore the thing. So if you were doing painting as an art, you would be doing it to kind of explore what it means to paint. You would be trying this and you would be trying that, or you would be investigating it, something like that. But you could do chemistry the same way. You could explore chemistry as an art, which means, hey, you're just going to like play around with stuff and see what happens when you put this stuff and that stuff together. Maybe that's not such a great idea in chemistry, so forth. Don't want to hurt yourself. But if you're just exploring it to figure out how this thing works in the world, that would be doing it as an art. Or exploring yourself. So you're exploring the thing or yourself. Now you're thinking, like, what do you mean yourself? Well, if you're doing the thing to figure out something about yourself, so maybe you're painting to help yourself understand your moods or something like that. Or, like, I don't know, you could do chemistry as a means of disciplining yourself. Can you organize data in a table or something like that? You're doing it to kind of figure out what it means to be a human being and so forth like that, or to maximize your ability. And we still see that today in the modern use of the term martial art. Because in martial arts, yes, you're studying combat, but in a sense, you're doing it to understand yourself. How do you control your emotions? How do you not flinch when your instinct is to flinch and something like that? So that would be a modern use of the term art as doing something to figure out what it means to be you or to help yourself get better as a person. Okay. Science, though, in the classical sense, means something that already exists as there's already known laws. So this might be after you study something as an art. Once you figure out how the thing works, then you put together a system or your understanding of the system. And what you're doing it is you're doing it to get exact results. So you're doing it to replicate something. So you could do painting as a science where you're studying how to paint with oils to exactly duplicate a famous historical painting like the Mona Lisa or something like that. You're doing it to make a perfect copy as best as you can to get the exact same thing. That would be doing painting as a science. Now, nowadays we talk about arts and science, we're talking about the thing that you're doing, but the classical sense of art and science meant how or why you're doing the thing. What we're doing is we're doing mathematics both as an art and a science of number. We're exploring number one, to kind of figure out what it is. I'm not just here to tell you this is this and that is that. Part of the joy of learning is figuring things out for yourself. I'm going to put you in situations or arrangements where you can discover the thing yourself, and you get much more an advantage of that knowledge when you figure things out yourself than if somebody just tells you. You kind of own it at that point because you figured it out on your own. Maybe with help, but you did it yourself. Or, we're doing mathematics to help train you as a human being, not just a job skill. It's helping you learn about yourself and discipline yourself. But we're also going to do it as a science, which means once you figure this stuff out, we're then going to apply it to practical situations and we're going to produce exact results. So that's what we're doing for mathematics. Now, number. That's the interesting thing. Mathematics deals with numbers. So, oh, by the way, before we go on, a peculiar benefit of mathematics is that the principles are demonstrable. They can be demonstrated. Hey, here's this principle of mathematics. Gee, I'm having a hard time kind of understanding that. Can you demonstrate it to me so that I can observe it? Yeah. And its conclusions are certain. Oh, you think the sum of the interior angles of a triangle is 180 degrees? Well, I'm not so sure. Here's a proof. We can show you. Oh, now I'm convinced. Okay. And once you get the information, the conclusions are certain. There's really no doubt in the end that 3 plus 5 is 8. You're not going to wake up tomorrow and it's wrong. It's or changed or something like that. The conclusions are certain. There's certain conclusions. Now, you may be uncertain about your application of the math or your understanding of the math, but that's not uncertainty in the mathematics. That's uncertainty in ourselves and our use of the mathematics. So we'll come back to this as time goes on. All right, so two things now. Two things numbers tell us. They only tell us two things. Anytime and every time you've got numbers that are being used to describe something, they're either describing quantity, which is how many things there are, or it's describing size, which is how big one thing is. So if you're in class, I usually ask the class, how many people are in the room? And sometimes we get an argument, somebody miscounts or something like that. Oftentimes people think I asked how many students are in the room, so they don't think of me as a person, but I'm a person too. Yes, teachers are people too. You got to listen carefully to language. Words mean things. But you simply count how many there are. Okay. Now, this is a discrete number. Discrete means there's no in-betweens. It's only whole number values. You can't say that there's 12 and a third people in the room. You can't say that there's 15.5 people in the room. Where's the third of a person? Like, even if you're in like in a terrible automobile accident and you lose all of your arms and legs and maybe an ear or something like that, like, how much of your body parts do you need to lose before you're no longer a person or you're just a partial person? Like, no, that doesn't make any sense. If you're alive, you're a person, okay? And if you're not alive, you're like, I don't know, you're a person in the afterlife or something like that. Like, maybe that's beyond mathematics. But it's discrete number. You've got to have whole numbers. Back in the 80s, there was some study that came out that said, like, this is average America. And it was like the average number of children in the family was 2.5 children per family. And we would always joke, like, oh, yeah, the Smiths, they only have half a kid. Like, they got Billy and Sally, and then, like, they got half of something. Like, what is that? And it's like, that's not what we mean. Like, we know that's not what you mean. But it's interesting to talk about. You can't have partial people. They're whole number increments. But size is something else. If you were in class today, I told the class, hey, I got on the scale this morning and I was 168. That's a number. What's it telling me? It's a measure of how big I am. 168 pounds, right? You have to have a unit for size. Size is a measurement of one thing and it has to have some kind of unit with it. You don't have to have a unit if it says how many people are in the room. You just give a number, 12. But size, okay, how big are you, Mr. Marsh? I'm 72 inches. Something like that, right? 72 feet? No, that would be too large. 72 centimeters? Nope, that's less than 3 feet tall. You've got to have a unit. But with size, you can have in-between values, okay? That's a continuous number. If your parents ever do the thing where, like, you stand up against the wall and they put a little mark on your head, how tall you are, and then, like, 6 months later they mark you again, and it's like a little thing that measures your growth. Okay. If you were 3 feet tall on one day and sometime later you come back and you're 4 feet tall, you actually must have been 3.5 feet tall at some point. You can't skip over that. That's a continuous number. So discrete and continuous numbers, quantity and size. And this actually, though, the one and the many, this is actually an important, even philosophical concept. There's a tension in the one and the many in all kinds of areas, not just in mathematics. Oh my gooseness, it's my phone, I'm so sorry. It's my alarm. Thanks for being patient with me. What was I saying? Oh, the motto of the United States is E pluribus unum, out of many, one, which means out of many different people groups, we have one nation. And how do you balance the rights and the privileges and the responsibilities of the many versus the rights and the... Is it just a straight democracy or is it a monarchy or like... There's a tension involved in this, so it's one of the many. We'll talk about that as the year goes on. I'd like to come back to that. Okay, now, This is something that's not in any textbook. Most of the stuff so far, you've touched on it. Although a lot of textbooks and a lot of classes, they talk about the details, but they don't talk about the obvious ideas that are behind the details. Like it's an obvious idea. Um, oh, it's at the top of the hour. I guess you get to listen to my clock. That's just part of what it means to do a math video class in my den. This is not part of a lesson plan, but anyway. 8. Was that quantity or size? I think it was size. How much time has progressed since noon? Wouldn't that be a continuous number? Wasn't it at some point 7:30? It wasn't such a bad interruption after all. Okay, maybe you've seen some of these things or you've thought about them. It's rare to find a math textbook or a class that actually comes out and says these things directly so that you're thinking about them. Most people kind of have an instinct and they're unaware of it. But when somebody finally says, this is how it works here and this is how it works there, they're like, oh yeah, that makes sense. I know that. And it's not a new idea. You just weren't aware of the idea consciously. But this next one, what does a sign mean? Positive or negative? I've never seen this talked about in any class before. I wish it was. It took me having to go to like high school, college physics to sort this out. Sign means direction. Anytime and every time there's a positive and negative sign, plus, minus, or something like that, it always means direction of some kind. Left or right of something, like on a number line. Above or below. Forwards or backwards. You could have clockwise and counterclockwise spin. Your bank account's got withdrawals and deposits and stuff like that. That's always plus or minus. Which direction are things moving somehow? Or where are they in relation to something else? Okay, so a sign tells direction. It's different from number. Okay, now there's two kinds of direction. There's direction of location, which means you're right or left of 0 usually, or you're above or below something. Okay, so like on a number line, we've got your 0 is the point at which you decide what sign things are. 0 has no sign. It's the reference point that determines sign of other things. To the right, you got 1, 2, and 3, and 4, and to the left, you've got also 1, 2, and 3, and 4. But when you go to the left, you have to put negatives on here because it's the opposite direction of these numbers over here. And I guess technically, if you're going to have negatives, you also have to have positives. These over here, it's positive 1, positive 2, positive 3, positive 4. Now, some things really can't have a direction, like my weight. I wouldn't say, my weight today is positive 164 pounds. You wouldn't say positive because there's no possibility for negative 164 pounds. It's just 164 pounds. In other words, there's something that doesn't involve any direction at all, your weight. Okay, that would be what it is. But you also have change. Now, when something changes, it's moving to the right or to the left. Oh, so if my weight changes, then I can put a sign on it. I was 168 today, and I have a plus 5 by the end of the week, so that's adding 5. It's increasing. Or I'm decreasing. I'd like it to decrease. But you get the point, right? So this is one of the examples I gave in class. Follow along here. I said positive 3 minus 5 is equal to what? And all the classes said like, oh, it's negative 2. And I'm like, what does that mean? Okay. So the positive 3 means that's your starting location. You're starting at positive 3 on the number line. Okay. Then this next part, minus 5, that's your change. What does that mean? It means move to the left, negative 5. So I'm going to move to the left. 1, 2, 3, 4, 5. Where's my final stopping point? Negative 2. Okay, so sign means direction, either direction of change or location. Now, absolute value is one of these things that I don't think is described very well at all. So I'm going to give you a simple, straightforward, Marshable definition for absolute value. It's really kind of simple. Absolute value just means how big's the number. I'm not interested in the sign. Only the number, don't care about the sign. Most math books say absolute value is the distance between numbers and zero on the number line. Yes, that's an example of how you would do it on the number line. You're not always on a number line with something. It just means how big is the number. So, for example, I'll do a little sidebar over here. Absolute value of -7. The vertical bars mean what is the absolute value of that. It's really asking you how big's the number only. How big's that number? 7 units big. Don't put positive there. It doesn't even mean +7. It means 7 without a sign. And what is the absolute value of +3? 3. Just take the sign off. Just strip the sign off. How big's the number? 3. That's all you need. Now, when you put this together in like a, I don't know, an expression. Let me see if I can get above my head here. What if I said 9 plus the absolute value of -8? You're like, well, okay, how big is -8? That would be 9 plus 8, no sign. But now there's the sign that tells you what to do with it. 9 plus 8, oh, that's 17. Okay, so sort it out. Now, only 3 comparisons between numbers. And you're probably aware of this instinctually because you've been doing it for a long time. But now we're going to talk about it directly so that it's in the front of your head and you're conscious of it. Okay? Numbers are either equal to each other, or one number is less than another number, or one number is greater than another number. Like, that's it. That's only the only 3 ways that you can compare things. And this shows up in questions where you're asked, Bobby's sales was such and such for the week, and Sally's sales were such and such for the week. Compare Bobby's sales to Sally's sales. People are like, I don't know what they're asking. Comparison. Are they equal to each other? Is Bobby's less than Sally's, or is Bobby's greater than Sally's? That's all you're asking you to do. And the kids are like, oh, that's so easy. I'm like, yeah, let's talk about this. So 5 plus 3 equal to 8. 5 less than 8. Please be sure that you interpret this here as 5 is less than 8. I don't want a second grade idea of, 8's being eaten by the alligator mouth, so 8's bigger. That's not how you read this. It's 5 is less than 8. That's how you read it, from left to right. This says 5 is greater than 3. You have to read it that way. The symbol means is greater than, or the symbol means is less than. Now, for most cases in your experience, 5 is greater than 2 is logically or mathematically equivalent to 2 is less than 5. But in terms of the idea, they're not the same thing. If I said 5 is less than 2, think about the grammar of the sentence. 5 is less than 2. Like, think of it in terms of words. What's the subject of the sentence? Remember this? Remember your nouns and verbs and predicates? The subject is the thing that you're talking about in the sentence. And the predicate is what you're saying about the thing. So if I said, the sky is blue, what am I talking about? What's the subject? The sky. Okay, what am I saying about the subject? You're saying that it's blue. That's different. Subject and predicate are different. If I switch the order of those things and I said, all that is blue is sky, you would disagree with that. You may say the first statement's true. Yeah, the sky is blue, but not everything that's blue is sky. So sometimes in language, there's a difference in the order of the words, and if you switch the order, it changes the meaning. Now, in mathematics, usually not. Maybe this is a little bit too technical. But the subject of this sentence here, 5 is greater than 2, is 5. I'm talking about 5. What am I saying about 5? You're saying it's greater than 2. Okay. If I hear and say this, if I say 2 is less than 5, the subject is now 2. I'm talking about 2. What am I saying about 2? I'm saying it's less than 5. There's a slight variation on that. I just want you to be aware of it. If you understand just the basics idea that they're not exactly the same when you say them with words, I think that's enough. Okay, so now on to the next page. If I can get my iPad to stop lagging. Okay, operations on numbers. There's 4 basic ones. Add, subtract, multiply, divide. You're probably settled with that. Exponents, though, are something that's maybe relatively new for you. An exponent is repeated multiplication. And so I have here my example of 3 squared is equal to 9. The 3 is the thing that's being repeatedly multiplied. The 2 tells you how many bases you've got. So one of the questions I want you to ask when you see exponents is, what's the base? It's important. Sometimes it's more than just the number here that's the base. Sometimes if you got parentheses, it's more than that. But this tells me I'm going to multiply 2 3s together. It's not 6. It's not 3 times 2. It's 2 3s multiplied. That's 9. The answer to an exponent is a power. Most people don't know that, but now you do. Okay. A radical or a root goes the opposite direction. A radical takes the power and says, what do you have to square it to get 9? Well, what number squared is 9? That's 3. So on the square root side of things, you would say the square root of 9, that's 3. But for some reason, they rename these parts. The thing that you're taking the square root of is now called a radicand, A-N-D as in delta. It really is the same thing as the power over here. We're just rearranging the question and answer parts. 3 is the base. That's the answer where it was part of the question over here. And then sometimes there's a number written right here in the little crook of the square root symbol. That's called the index. Now, when you do a square root, you don't write anything there. It's understood that it's 2, even though it's like invisible. You don't have to write that, because if you don't write it, then everybody knows that it's 2. But when you do things like cube roots, the reverse of a cube, or the reverse of a 4th power, which we'll do in this class, you have to write a number right there. I'll give you an example of that here in just a second. Okay, and then we went over to completing these table of values here. These are all the perfect squares. If you square the number right here, if x is 1, what's 1 times 1? Well, that's 1. If x is 5, what's 5 squared? This is 25, right? You square the number is 25. So you should be able to do this down through the column. Here's all the perfect squares on this middle column right here. Okay, I have to talk about 12 squared is called a gross. 144 is a gross. It doesn't mean like disgusting, although that word has come to mean that. A gross usually meant something that was 12 times 12. It was 12 squared. A dozen is called a gross. Like that's the name of the number. Okay? And eventually it became to mean something that was just excessively large. Oh, it's not a dozen, it's a dozen. How many donuts did you eat? A dozen? Oh, no, I ate a dozen. And then that became, it was so large, it's disgustingly large. And then it became just kind of like disgusting. Anyway, every time the number 144 shows up, I always say, ooh, gross. So, yeah. Okay. Actually, powers of 10 are interesting. The place value is based upon powers of 10. Then the whole number system is based upon powers of 10. You can think about that. Okay, you can fill that chart out on your own. Now, real numbers are split into 2 groups. Let's go over here onto the right side. 2 groups. One group's rational, the other group is not rational, which means ir. So whatever's not in this group is in this group. This group's got all the extra stuff, okay? A rational number, ratio. Do you see ratio written right there? R-A-T-I-O. A rational number is a number that can be written as a ratio or a fraction, although they're not exactly the same thing, ratios and fractions. But you can write it as a fraction of integers. Integers is the proper math word, but most of you understand when I say whole numbers. Mathematicians have a special definition for whole numbers, so you really can't say whole numbers in math class. The proper word's integer. The educated person says integer. Integer would be positive and negative whole numbers. For a mathematician, whole numbers are just the non-negative ones. Don't sweat that. Know what an integer is. So all of these here are examples of integers. Negative 3/4. Can you write that as a fraction of whole numbers? Yeah, there it is. 5. How do you write 5 as a fraction of whole numbers? 5 over 1. You know that, right? Square root of 36. What is that? That's actually equal to 6, which is a rational number because you can write it as 6 over 1. Okay, negative 12. I want to talk about 2 different things. One of them is that when you do a rational number as a decimal, it terminates, it stops. What is 0.25 as a fraction? Well, that would be 25 over 100, and then that can reduce down to 1/4. There's your reduced fraction. When you take a rational number and you make it a decimal, it will either stop on its own, it will terminate, or it will repeat. Okay, so here's the example of the repetition. 1/3, what is that as a decimal? 0.3333333333333 goes on forever. You might write that as 0.3 with a bar over the top. Or if you want to write it out like dot, 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 you've got to do the dot, dot, dots down there. Those are ellipses. They mean it goes on forever in math. The repeating goes on forever in math. You can do a decimal over a whole number if you just multiply top and bottom by 10. 21 over 9, you multiply top and bottom by 10, you get 21 90ths. That's a rational number. Okay. So rational numbers, as decimals, they terminate or they repeat. And again, an integer, what would be what you and I would call positive and negative whole numbers. Do you see whole there in quotation marks? Whole numbers. This lesson's been at least 15 minutes long. Anyway, so irrational numbers is just everything else that doesn't fit into that group. Okay, square root of 7. You can't write the square root of 7 exactly as a fraction of two whole numbers. You can't write the number pi exactly as a fraction of two whole numbers. Now, I was under the mistaken impression that you could, because at some point in my math background as a kid, I was told to use, like, what is it, 22 sevenths? We were told to use 22 sevenths. And so I remember being in class and arguing with the teacher, which you got to be careful when you argue with the teacher. Like, maybe you're right, but like chances are you probably should listen first before you speak. But I said, oh no, 22 sevenths is pi. You're wrong. And I got corrected. Oh no, that was just an approximation. That's not actually the true exact value of pi. You're going to say, oh no, it's 3.14159. No. That was just an approximation. The real value of pi is irrational, the perfect number. Okay, so in higher math classes, you have to give like exact answers. Don't want your decimal approximation. And so sometimes you just leave pi in the answer, like you have to write the symbol. So as decimals, they don't terminate and they don't repeat. So for example here, the square root of 2 is approximately, not equals, that symbol there, the squiggly lines, in arithmetic, not geometry, that symbol in arithmetic means approximately. 1.414213.5. Notice none of these digits repeat, but the ellipsis there says it does go on forever, but there's no repetition. Okay, so rational and irrational and integer are the three main ideas for this. Almost finished. Placing real numbers on the number line. Here's a number line that I've got with the structure along the bottom. Here's 0, here's 1, 2, 3, 4, 5. Here's -1, -2. And then along the top, I'm showing you where certain numbers go. -3.5, to the left of 0. 1, 2, 3, and a half. Notice it's to the left of 3, of the number 3. But if we had been on the right side, +3.5 would have been to the right of 3. So be careful which direction you're going. When you're on the left side of 0, all of these numbers have got the direction stuff reversed. Okay, so -0.7. That's between 0 and -1. So it's between these here. It's about 7/10 of the way through. +1/3. As a decimal, that's 0.33333. That's like about right here. Square root of 9, what's that? Well, that's just plain old 3. So there we go. Square root of 20, that's not like an integer. It's a non-terminating thing. What is that as a decimal? Like if you looked at the square root of 20, you're like, yeah, I'm not really even sure how big that is. Use a calculator, get it to a decimal. Oh, it's about 4.47. That's about 4.5. So maybe just a little hair less than 4.5. 28/5. I don't know where that really is either on the number line either. You kind of have to have them in decimal form to place them on the number line. Just take 28 divided by 5 on your calculator. It's 5 and like 5. What is that as a decimal? 5.6? 5.6? 5 3/5. So it's between 5 and 6. 5.6. Okay. So that's kind of it. By way of review real quick, we'll summarize and then we'll be done. What's mathematics? The art and the science of number. You need to have that answer memorized. I'm going to ask you about that. What two things do numbers then tell us? Numbers tell us either how many or how big one thing is. Okay, quantity or size. I would actually prefer this definition here. How many things there are and how big one thing is. That's better than just giving kind of like the precise nominal word replacement, quantity and size. This explains it. What does a sign tell us? Direction. 3 comparisons between numbers. Equal to, less than, greater than. And then the rest of this is just some review and some details and stuff like that. Okay, that's all for today. I don't know how to end the video except to say, so long, farewell, see you in class sometime later. Bye bye.